The other topic in this unit are reaction mechanisms. And there's a couple things that are really important to understand. And I do not want you to get confused with the beginning part of this unit. So far, what we have seen is that rate laws are experimentally determined. And I told you that if you have your rate equals A to the A, rate is equal to Ka to the M, and your reaction is AA goes to products, that A does not equal M. Okay, so that's what we've done so far. What I'm about to tell you is the exact opposite. So if you have a reaction mechanism, which are the individual steps of a reaction broken down into single collision changes. Before we were talking about a reaction that could have a bunch of collisions, a bunch of steps, a bunch of intermediates. Here we are talking about single collision changes. These are called elementary processes. And these have different rules. So if you are talking about a reaction mechanism, a list of single collision changes, you can figure out the rate law without experimental data. Some rules for this that I will show you in some examples are that your reaction mechanism must be consistent with the stoichiometry of the net reaction. So your mechanisms have to add up together to equal the net reaction, and then they must agree with or account for the experimentally determined rate law, which again, I will show you what that means. All right, so if you have an elementary process where A and B are colliding in a single collision, sorry, I wasn't sure if there were two S's or one in collision. I think there's only one. Then you can say that your rate is equal to K, A to the M, B to the N, and you can say that M is equal to A and N is equal to B. So only if it is a single collision. These collisions have terms determining describing the number of molecules involved in the collision. So a unimolecular collision is where there's only one molecule involved and it kind of falls apart. Bimolecular would be two molecules colliding. Termolecular would be three molecules colliding. It's very unlikely for more than three molecules to collide in a single step with the proper orientation. So usually we do not propose single step collisions that involve more than three molecules. Some of these can be reversible, some can reach equilibrium. There's something called an intermediate, which is something that appears and then disappears. So let's say we have the reaction A plus B. Let's do A goes to P. And we say that this mechanism is composed of two steps, A going to B and then B going to P. Then the intermediate in this case would be something that is made and then goes away. So B would be an intermediate. Okay. Other thing that's really important to understand is that the rate determining step is the slowest step in the overall reaction. It's like the bottleneck, and we can assume that the rest of the reaction happens so quickly that it is negligible to the overall rate. This is like, at least for me, when I try to get home, my rate determining step is leaving the parking lot and getting on to Westerly because of the traffic and the buses. And once I do that, it's so fast to get home. Okay, so here's an example. Let's say we're talking about nitrogen dioxide and carbon monoxide reacting to form nitrogen monoxide and carbon dioxide. And we have a proposed mechanism. There's a slow step, which is NO2 and NO2 colliding. to make NO3 and NO. So essentially one of the oxygens coming off and going to the other one. And then after that, there's a fast step where the nitrogen trioxide and the carbon dioxide react or collide, and you make nitrogen dioxide and CO2. So first thing we want to check is that if we add up these two steps, do they equal the stoichiometry of the overall reaction? So I see that NO3 is an intermediate. It is canceled out. It does not appear in my overall reaction. My NO2, one of those goes away. And what I'm left with as my overall stoichiometry is NO2 plus carbon monoxide goes to NO plus CO2. So my stoichiometry matches up. All right. So that's great. My stoichiometry works. The other thing we need to check is to see if the experimentally determined rate law matches up with the rate law of the proposed mechanism. And what we are going to assume is that the slow step determines the rate. So I am going to look at the slow step of my proposed mechanism and see if the rate law of this single step matches up with the rate law of my overall reaction. So when we are dealing with an intermediate process, we can now use the coefficients in that step. And so what I see is that my rate here is going to depend on the concentration of NO2, and there are two NO2 molecules, so it's going to be NO2 squared. The rate of my slow step equals the rate of my overall reaction. Oops, sorry. So this is good. This means that this is a plausible mechanism. It does not mean that it is the correct mechanism. You cannot prove that things are correct in science. You can only disprove ideas. But this is plausible. Okay, so this is relatively simple when the slow step comes first. You just write the slow step out as a rate law. You use the coefficients in the slow step to come up with the exponent in the rate law, and then you check to see if it matches the experimental rate law. Okay. If the slow step is not the first step, there is a little bit more math to do. This is called a steady state reaction. Or steady state equilibrium. And in these reactions, there's going to be a first step that is fast and reversible. And that is going to establish an equilibrium before all of the, and when I say product here, what I really mean is intermediate, is consumed. So before the slow step happens, the fast step is going to reach equilibrium. Okay. So here's an example. Chlorine, CHCl3 makes HCl and CCl4. Okay. And we have an experimentally determined rate law. What's interesting is there is a fractional exponent, so we'll see how that happens. Here is a proposed mechanism. It's 3 steps. There is a fast step that reaches equilibrium, a slow step, and then another fast step. First thing we want to do is check to make sure that the stoichiometry of everything works out. So I see that my 2Cl is consumed. I see that CCl3 is consumed, and my net reaction is equal to, that's good, my stoichiometry works. Next thing we need to do is check to see if the rate law of my mechanism is equal to the experimentally determined rate law. So just like before, I'm going to start with my slow step. And I'm going to say rate is equal to concentration of my reactants raised to their coefficients. Okay. There is a problem here, and that is that Cl is an intermediate, which means that it cannot show up in the rate law. The reason why it cannot show up in the rate law is because it's really hard to determine the concentration of chlorine because it's not something we are adding to the reaction. So what we have to do is use this fast equilibrium step to determine a relationship between the Cl2 and the 2Cl. So what I can do is I know that if a reaction is at equilibrium, and this is something we will review, that for this fast step, the forward reaction is equal to, the rate of the forward reaction is equal to the rate of the reverse reaction. That's what it means to be in equilibrium. So what I can do is I can write rate laws for the forward reaction and for the reverse reaction. The rate of the forward is going to be equal to K times my concentration of Cl2. And I'm going to call this Kf. The rate of my reverse reaction is going to be equal to Kr, rate constant of the reverse reaction, times concentration of Cl squared because of the 2 in the equilibrium. Okay. My goal is to rearrange this and solve for the concentration of chlorine. And we are going to then substitute that into our slow rate law. Okay, so I'm going to treat this just like an algebra problem. I'm going to divide both sides by Kr, and I'm going to take the square root. So what I end up with is concentration of chlorine. Actually, let's do this in 2 steps, is equal to Kf over Kr, concentration of Cl2. And then I can take the square root of both sides, and I get concentration of chlorine is equal to Kf over Kr times the concentration of Cl2. So I'm going to take this and I'm going to substitute it into my slow rate law. I'm running out of space, but that's okay. Sorry, I forgot a K here. K, square root Kf over Kr, concentration Cl2, times CHCl3, which I do not have space for. Sorry. Beautiful. Okay. Let me just rewrite that. I am going to lump all of my rates constants into a single K. You can either call this K prime to indicate it's a new K, or you can just call it K. Either one is fine. And what we get is rate is equal to new rate constant, which is equal to K times the square root of Kf over Kr. We totally don't care what any of those numbers are. All that we care about is that it's a constant, times concentration Cl2 to the 1/2, concentration of CHCl3. So this is one of the ways that we can get fractional exponents. And it turns out that my rate of my mechanism is equal to my experimentally determined rate law. So that's good. That means that this is a plausible mechanism. Okay, if you go to my slides, you can see I have all of this stuff that I just said typed. You can see I go through this, so if you can't read my handwriting or you want to look at it again, this is all on the slides on the agenda. Okay, and we get something that agrees with the experimentally determined rate law. Okay, something important is that we did not prove that this is the correct mechanism. We just showed that we cannot rule it out. There could be other mechanisms that are also plausible that fit the experimental rate law. To determine which one is a better mechanism, we would need to do more experiments to try to disprove one of the mechanisms. This is very similar. I always think of like stat, because I'm a stat person. You cannot accept your null hypothesis. We just failed to reject it. So we failed to reject this mechanism, but we are not like accepting this as the correct mechanism. All right, some vocab words. I think the rest of this is not too bad. I think we did the hard stuff. A catalyst is something that appears in the starting material and then is regenerated by the end of the reaction. It does not show up in the net reaction, but it can be in the rate law occasionally. That often trips people up. There's no problem with a catalyst being in the rate law because we can measure the concentration of a catalyst. We know how much we're adding. Intermediates are products that are consumed in further steps. Just like catalysts, products do not show up in the net reaction, but different than catalysts, they may not be in the rate law. So if we have an example here, A plus B goes to C plus D, and we have a two-step proposal, we can see that there are two compounds here that do not appear in the net reaction. There's F, and there is E. F is present at the beginning. It is regenerated by the end. So this is considered a catalyst. Whereas E is something that is created in one step, destroyed in the other step. And so this is an intermediate. Both get canceled out. Catalyst was there from the beginning. Intermediates are made. Okay. Other properties about catalysts. A catalyst not only lowers the activation energy, but it can also change the reaction mechanism. So what you can see here, these two peaks correspond to a two-step mechanism. If you only have one peak, that corresponds to a one-step mechanism. If we were to zoom in on the second, sorry, let me redraw that maybe. So this is a catalyzed energy diagram. You can see that actually in both cases, energy of the reactants and products doesn't change. This is an endothermic reaction. It's going uphill. The valley between the two peaks is where the intermediate is. So this is something that is produced in the first step and then is consumed in the second step. So if we had the same reaction mechanism as before, so A plus B, let's leave out the catalyst, goes to C plus E, and then E goes to D plus F. A plus B, D plus F, products, reactants. Sorry, let's actually include the catalyst because this is the catalyst pathway, so that probably makes more sense. So A plus B plus F are reactants, D plus F are the products. C plus D plus F. And then the whole thing that I really wanted to draw was that E, my intermediate, appears at the valley between the two peaks. This is transition state 1. This is transition state 2. Activation energy goes from the reactants to the top of the hill. So this is activation energy 1. Here is my activation energy 2 from the reactants, which is the intermediate, to the top of the hill. And then the activation energy controls the rate of the kinetic. So in this case, EA1 is a lot bigger than EA2, which means it's going to be a lot harder to get the first step to happen. So this is going to be my slow step. And this is going to be my fast step. So the larger your EA is, the slower your step is going to be. Here's another example where maybe the catalyst makes it into a 3-step reaction. The enthalpy is the same for both ways, but the activation energy drops. Okay. Here's another example. So this is an exothermic reaction. Here's your first EA. Here's your intermediate. Here's your second Here's your second EA. And this would be a 2-step mechanism because there are 2 peaks, and the first step is the slow step, second step is the fast step. AC, in this case, is activated complex, or the transition state. So something you could see as a problem would be draw an energy diagram for an endothermic reaction with a slow second step. First thing we know is that if it's endothermic, the net change has to be uphill. So I'm going to draw my products at a higher energy than my reactants. This is 2 steps, so it's going to have 2 peaks. And if it has a slow second step, it's going to have a large second activation energy. So this is a common AP question. There are many ways you could do this. I might draw something really exaggerated. Actually, let me... like this. So it's endothermic, it's 2 steps, and we have a large second activation energy. The problem might then also ask in a dashed line, draw a catalyzed 1-step reaction. So what you would do now is there would only be 1 peak. Your reactants are still at the same energy. Your products are still at the same energy. It's catalyzed, though. So you want it to have a lower activation energy. And maybe I still make it have there we go. That's all that I wanted to do for the notes. You have some problems in the handout that you can do. You can work on the book work. There's a copy of the chapter online. Write down any questions you have, and we will talk about them next week. All right, have a fantastic weekend, and I will see you all on Tuesday.